We'll proceed in vector summation and integral theorem. Vector summation and integral calculus, we are proceeding the discussion into which, and then we are calculating the Taylor series. We are calculating the Taylor series in multivariate. Multivariate Taylor series is like fxy, fxy equal to 1. Okay, what is fxy? Fxy is an equation for the three dimension. It resolves into a surface that is called fxy. It resolves into a surface. Can you give one example of fxy? Okay, you are trying to turn fxy into multivariable Taylor series. Taylor series means, can I demonstrate, can I write a fxy into a series of multivariable polynomial equation like x to the power 1, 2, 3, 4, x to the power 0, 1, 2, 3, 4, y to the power 0, 1, 2, 3, 4 together. Okay, that is the concept that we are pursuing, mind blowing, amazing. And what is fxy? If I talk about fxy, then fxy is a concept that gives a surface. Okay, if this is x-axis, then this is y-axis, where x is considered as independent and y is considered as dependent. Depend in the sense that if I have a curve like this, if I have a curve like this curve equation is dependent. This curve equation fx equal to, this curve can be sin x, fx equal to sin x. This curve can be fx equal to sin x. This is fx equal to sin x. This is fx equal to sin x. Fx means height. At any x, what is the height? Height is y-axis. If this height is variable with the x-axis, depend upon x-axis, then this fx is considered a depend upon x, function over x. Okay, this is two-dimensional and this is x-axis and this is y-axis. If I turn it down, then it becomes x-axis and this will become y-axis. This becomes xy plane. This becomes xy plane, where x-axis and y-axis are independent to each other. They are not dependent upon each other. Y-axis is dependent upon x-axis. If I make it a plane, xy axis, and this is xy plane. This is xy plane where this is x-axis and this is y-axis. They both are considered as independent to each other. There is no formula where we have fx. Okay, there is one formula called fxy. This is fxy, a surface that is above the xy plane surface. What is fxy? Fxy is the height from this xy plane. If this is xy plane, now there are many x comma y. Many x comma y is there. At any x comma y, what is the height? That height is called fxy. At any x comma y, what is the height? That height is called fxy. Fxy is also termed as z value. Okay, like I have a sphere and this is x-axis and this is y-axis, this is xy plane, and this sphere is above the xy plane. Okay, if I take any point here x comma y, any point x comma y, and draw a vertical line, it will hit it somewhere like that. Or if I see from the top, then it will match a circular region on xy plane if it is a sphere, and that circular region has a lot of x comma y, and for that x comma y, if I go up, if there is a xy plane, I take any x comma y, if I draw a vertical, it will hit somewhere. X comma y, I draw a vertical, it will hit somewhere. Draw a vertical, that is hit somewhere. For any x comma, what is z value? Height, that is fxy. Okay, can you give example? Very simple. For the sphere, example is z equal to, that is fxy equal to square root of a square minus x square minus y square. If I say plus minus square root of a square minus x square minus y square, this is a full-fledged sphere where half of the sphere is above the xy plane and half of the sphere is below xy plane. Z equal to or fxy equal to plus minus square root of a square minus x square minus y square. No, no, no. It is something like, I know it. What you know it? X square plus y square plus z square equal to a square. That is the equation of a sphere. Yeah, this is what. Where x and y are independent to everything and they are not dependent upon anything. I don't have anything called y equal to some function over x. Y is not dependent upon x. Whereas z is function over x and y. Z is dependent upon x and y. So the better way to represent a sphere is fxy equal to plus minus square root of a square minus x square minus y square. If I say x square plus y square plus z square equal to a square, this is the algebraic equation. But the way we are saying fxy equal to plus minus square root of a square minus x square minus y square, this is something called calculus algebra, where we have clear distinction. On equal sign, left side is dependent, and on equal sign, right side is independent, and x, y are independent to each other. Can I write the square root of a square minus x square minus y square equal to, that is fxy, equal to a set of polynomial equation? Set of polynomial equation. What is set of polynomial equation? A0, A0, that is a number, plus A1, and in some terminology in x and y, x to the power 1 and y to the power 1, A1, and in bracket, x to the power 1, y to the power 1, some plus minus or whatsoever, plus A2, and in bracket, x to the power 2, y to the power 2, x into y, that is also power 2 only, x into y, something, plus a3, x to the power 3, y to the power 3, x square y, xy square, plus a4, x to the power 4, y to the power 4, and then a to the power 3, sorry, x to the power 3y, x square y square, x y to the power 3, like that. Can we write in a polynomial equation? This is called Taylor multivariable series. Okay, to find it, now we are going through a different kind of methodology. One methodology that what we have implemented, first we'll talk about it, and there our volume methodology is based upon it. What methodology that we are incorporating is, let's find the Taylor series for single independent variable. So single independent variable Taylor series is fx equal to a0 plus plus 1 plus d fx equal to a0 plus a1 dfxy by dx into x plus a2, I'm sorry, fx equal to a0 plus dfxy by dx at x equal to 0 into x plus dfx d2 by dx square at x equal to 0 into x square by factorial of 2, like so. This is the single variable Taylor series. And we have proved it by calculating the area. What is calculating the area is, okay, what is fx is? Fx can be a circular region. This is fx, where this is x-axis. What is fx? Fx equal to plus minus a square root of a square minus x square. That is y. At any point, this is x-axis, at any x-axis, at any point in x-axis, what is the y? Y are in two directions. If I see this circle, y are in two directions. One is plus y and one is minus y. Plus minus square root of a square minus x square. This is x, this is origin. Then that will give the 2y. This is the equation of y. Can I write a square root of a square minus x square? A square minus x square root as a0 plus a1 x to the power 1 plus a2 x to the power 2 plus a3 x to the power 3 plus a4 x to the power 4 plus like that. Is it possible? Okay, to make it possible, then what we did is take any curve. So we took a very typical curve like this. Okay, this is x-axis. A very typical curve like this. Consider this is the curve. This distance here to here origin is x, and this is y-axis. Now the interception on the y-axis like this is function over x. This is function over x. Okay, the interception on the y-axis at x equal to 0, this interception at x equal to 0, fx equal to f0. What is the interception at y-axis? If I talk about this interception, this length, then it is fx at x equal to 0. This length is fx at x equal to 0. So I would say what is the surface area? What is the surface area of this fx? Surface area means if I draw a line like this, then underneath this line, what is the surface area? That is fx dx integration 0 to x. 0 to x fx dx is the surface area underneath. Can I calculate this surface area? Can I calculate this surface area as combination of many surface area? That is the question that is hitting anyone's mind. What is the surface area combination? First surface area is the surface area of a rectangle where the height is fx at x equal to 0. Means this is the height. This is the height. This height multiplied by the x, that will give the area of a rectangle. That is, height is this much, and then this, and then this. This is the area of rectangle, that is fx at x equal to 0 into x. Makes sense? Okay. What is problem here? Problem here is that we calculated area of a rectangle which has a height this much and width this much. This portion we calculated extra, where the intention was to calculate this area only. So I have to subtract this area. To subtract this area, now I will say that consider there is a triangle like this. There is a triangle like this. Means if I calculate the tangent line at x equal to 0, then this is the tangent line at x equal to 0. This line will go like this, and it will intersect line like this. Okay, in that fashion, it will form a triangle here. Okay, this will form a triangle here like this. Tangent at x equal to 0, and top side is length and this side is this. It forms a triangle. If I subtract the first rectangular area and with this triangle, more or less I'll get area underneath it. Okay, what is the area of this triangle? What is this line? This line is dy by dx at x equal to 0 into x. This is the vertical line. If I talk about this line, then it is dy by dx. This line slope is dy by dx. Okay, I can say this line equation is dy by dx into x. That is nothing but the vertical component we get. I believe it is all right. Okay, so dy by dx into x will give the vertical component. If I multiply vertical component with the horizontal component, I get the area of the triangle if I divide it by 2. 1 by 2 dfx by dx at x equal to 0 into x, that is the y, and then multiply by x. This is the area of this. I can say fx at x equal to 0 into x, that is the area of rectangle, minus 1 by 2 dfx by dx by dx into x, that is the y. Dfxy by dx into x is the y into x by 1 by 2 is the area of triangle, minus. Then someone would say that you missed out this reason. You are trying to subtract this rectangular area minus this area that is above this line. If you draw a tangent, if you draw a tangent, hop, hop, hop. If you draw a tangent, then this area is a triangular area. You subtracted from this rectangular area, but you missed this area. You have to subtract this area also. Then if I take first derivative, then it is a derivative. First, if I take first derivative, then in this line has a composition of many algebraic, many polynomials. This line, what we see, it has a component of many polynomials. It has component of many polynomials. Make sense? Okay. So first component is flat line. Second component is a slant line. Third component is dual derivative. This is the zeroth order derivative. This is the first derivative. Second derivative, if I take this, then I'll consider this line as a y equal to x square or something like that. If I take dual derivative, means if I calculate first derivative itself, it will be an algebra. If I take again a derivative, dual derivative, then it will come little down. If I take zero derivative, then it will be a flat line. If I take one derivative, then it will be a slant line. If I take dual derivative, then it will talk about bigger slant. This is what we want. So that this remaining region is this that we can tackle. Like this, if I take dual derivative, then if I take dual derivative, then remaining area I will calculate. Still, there will be area down the line that will be missing in the first subtraction. So key point is if I'm trying to calculate area beneath this line, then first I calculate the area of a rectangle. Then I said, oh, I'm sorry. This area I calculated extra. To subtract this region, I took the first derivative and subtracted the area of this triangle. Then I saw this area is missing. This area is missing. Then I took dual derivative little down and then calculated the area of this. Then again I said little area is missing. Then I took triple derivative and calculated the area of this. So this is what I keep doing. Okay, so fx dx integration, that is the area under the curve, equal to fx equal to 0, fx at x equal to 0 into x plus 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 dfx by dx into x, that is the y, into x, okay, into x divided by 2. Or someone would say, isn't it like that 1 by 2 dfxy by dx into x? X is a constant, right? I believe it is a constant. If it is a constant, though it will not be a constant. Okay. No, it is a constant. Well, it is a constant if we take x f dfx by dx at any point x. Mind it, that's why I have brought this discussion deliberately. This is different than if I deliberately I take a triangle. This is a line if I take and if I do dfx by dx, it will come as a constant. That is for sure. If this is a straight line. Okay, but if I take a curved line, if I do dfx by dx, then it will not be a constant, it will be a variable. I am taking at x equal to 0. What is the line? At x equal to 0, then what is the line? Otherwise, if that tangent is a variable and that will come in algebra, dfx. Like, consider I have a equation like fx equal to sine x or fx equal to square root of a square minus x square, the circle. If I do single derivation, then it will become minus x by a square root of a square minus x square. That itself is an algebra. That in itself it is an algebra. If I took dual derivative of it, it will come again an algebra. If I took triple derivative, it will come again as algebra. Okay, if I am calculating what is this single derivative value at x equal to 0, at x equal to 0, okay, then it will lead to a Maclaurin series or whatsoever. But this is how it is. So if I calculate, so we are calculating the triangle where we take the first derivative. And if I take first derivative and then calculate the value at x equal to 0, that will lead to a constant value. That will lead to a constant value. So what I am saying is dy by dx at x at any point x, that will be a constant value. Okay, if that constant value, if multiply by x and then multiply by 1 by 2, it will behave like a flat line. If I differentiate a slant line, then it will result into a constant value. Constant value means flat line. Means more or less we are trying to calculate area of another rectangle which has a base of x and height as 1 by 2 dfx by dx at x equal to 0 into x. Okay, anyway, what is the third component? First component, second component, third component. If I'm trying to calculate third component, that is the area underneath it, this is the area of rectangle minus area of triangle minus area of another component, that is dual derivative. If I calculate dual derivative and get the value at x equal to 0, okay, dual derivative means if I take first derivative, then it will be a slant line. It will be more or less like a slant line. If I have fx equal to x square, if I take first derivative, it will come in x. More or less, it's a slant line. If I take dual derivative, it will come as a flat line, area of a rectangle, where width is x. So if I take first derivative, then more or less it will come in arena of a triangle. If I take first derivative, if I take first derivative, then it will come in arena of a triangle. If I take second derivative, then it will come in arena of a rectangle. Okay, two derivative. First derivative, if it will lead to divide by 1 by 3. Then it will come in arena of a triangle. Then if I do again a derivative, it will come in an arena of 1 by 2. The way we are saying, it will become 1 by 3 into 1 by 2 into d2 fxy by dx square at x equal to 0 into x into x. This is the horizontal component when we are calculating area of a rectangle, then multiplied by the x. Okay, this is the concept. This is different. We are trying to simulate a condition where calculating the area of a shape where we have y equal to x square, but it is not exactly like that. We have the line which is a mixture of very high degree of polynomial. We are doing double differentiation. It is different than taking a plain line y equal to x square. Okay, for that, if we are trying to calculate the area, someone can proceed on this. We are not stopping. Someone can proceed on this. But whatsoever, it will be 1 by factorial of 3 d2 fx by dx square. If someone say, if you're really trying to calculate area of y equal to x square, then it will be x to the power 3 by 3 rather than factorial of 3, what you are saying. This is not exactly that. That is the difference. This is not exactly that. The line we are talking fx is not x square. We are taking double derivative. Through double derivative, we are trying to calculate some area. It is not that we are finding area underneath a line that is y equal to x square or any constant into x square. So it is different. It is something different. Okay, in that fashion, we are taking double derivative. If we take double derivative, then whatever is the component is, the component will become as a coefficient two times. If I take x to the power n as double derivative, x to the power n as double derivative, then coefficient will be n into n minus 1 two times. If I take integration of x to the power n minus 2 two times, then first time the division will be n minus 1. Then next time division will be n. Two times divisor will come. Makes sense? If I take dual differentiation, then coefficient will be two times. If I take integration two times, then coefficient denominator will come two times. Similarly, if I am calculating the area by calculating dual differentiation, that area that is integration, there the denominator will come two times. Makes sense? Now we have 1 by 3 into 1 by 2. Similar to if I have something x to the power 3 and if I calculate differentiation, it will be 3 into 2 that will come outside. If I have x, I am trying to calculate integration two times, then it will be 1 by 2 one time and then 1 by 3 next time, two times. Okay, so it will be 1 by 3 into 1 by 2, factorial 1 by factorial of 3 d2 fx by dx square at x equal to 0 into x square. That is the one component multiplied by x. That is the width. That is the area. Plus whatever, or someone say minus whatever. Okay, this is the way we calculated the area of a Taylor series. Now left side we have fx dx, that is the actual area integration, and right side we have whatever we have done. If I differentiate, we get fx here. Fx equal to f0 into x, differentiation f0, plus 1 by 2 dfx by dx at x equal to 0, that is a constant, into x square. Differentiation is 2x, 2 to go away, dfx by dx into x, plus x to the power 3, 3 outside 3 and factorial of 3, 1 by factorial of 2, d2 fx by dx square into x square. Like that it will go on. This is what we have proved. Anyway, now we will prove, so we will complete this in any fashion. Okay, now the concept is that can we prove the kind of concept of three-dimensional Taylor series through this way. Three-dimensional Taylor series through calculating the area. So in three-dimensional Taylor series, there is no area because we have XY plane, and on top of it, XY plane, I have a surface. So underneath the surface, there will be a volume. Okay, rather than surface area, there will be a volume. Okay, to have the volume, what is the volume if I have a surface area? Okay, if this is the XY plane and this is the surface area on top of it, okay, then what is the volume of this surface area? The surface area cannot be this flat the way it looks like. Okay, surface area the way we did in the two-dimensional. The surface, if I cut the surface area in XZ plane, then it should look like this. The way we did in two dimensions, ZX plane should look like this. If I cut in YZ plane, it should look like this again. Okay, what I'm trying to say is consider this is x-axis and this is y-axis. This is origin. This is x-axis and this is y-axis. Now, if I cut any surface, consider this is a surface. Surface is like this. Surface is like this. If I cut this surface in xz plane, if I cut this surface in xz plane, if I cut this surface in yz plane, if I cut this surface in xz plane, then there will be a curve like this. If I cut this surface in yz plane, then there will be a curve like this. If I see from this perspective, then it will look like this only. Or if I see from this, it will look like this only. If I rotate this, then that will be the surface it will form. Makes sense? Consider that is a very, 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 very kind of different kind of surface we have. Okay, from XZ plane it looks like this. And similarly, if I see from here, then it will look like this. Okay, consider in that fashion of a surface. Now to have the area volume of the surface, we have to calculate fxy dx dy integration or dxy plane. Fxy dxy plane. Earlier surface area was fx dx. It is fxy dxy plane and integration, that is the volume under the surface, equal to what is fxy at x equal to 0, y equal to 0. What is fxy at x equal to 0, y equal to 0? Then it is fx equal to 0, y equal to 0. Whatever it is, that is the height at x equal to 0. Means if this is the origin, then at this origin, what is the height of the surface? That is fxy at x equal to 0, y equal to 0. If I multiply this with x, consider along x-axis I have a distance of x. Along y-axis I have a distance of y, and my surface is above. My surface is, I'm calculating the volume under x and y only, not outside x. Then what is the volume when fxy when xy equal to 0? That is the height. What is the height at x equal to 0, y equal to 0? Fxy at x equal to 0, y. F00, that is the height, multiplied by x into y. On x-axis, x distance, on y-axis, y distance. If I multiply like this, then it will give the volume. But that volume may not be the correct. If I say my surface is like this, if I say my surface is like this, and this is the height at the origin, from my side, if I take this is the height at the origin, then full surface is below it, but I am taking the full volume. F00 multiplied by x and y, full volume I am taking. Someone will say you have to subtract. You have to calculate the volume underneath this surface, but you calculated volume completely. You have to subtract this region. To subtract this region, then what will be the volume? Let's take the single derivative. That if I take in exact plane single derivative, then it will be this tangential line. If I take yz plane single derivative, it will be this tangential line. What is the surface that will form if I take single derivative? Then in xz plane, it will be like this. And in YZ plane, it will be like this. What is the volume that I have to subtract now? Okay, to have that, let's take a surface and keep y constant, and then take this down. Keep y constant and take this down. This is the volume. How much this volume is? What is the surface area of xz plane? If I cut like xz plane, this is a triangular region. That is a triangular is a surface in area in xz plane. Whatever the surface area is multiplied by y, you will get the volume. Okay, then that volume is 1 by 2 dz by dx into x square. That is the surface area into y. 1 by 2 dz by dx x square into y. That volume. Now keep this constant and tilt the y. That is the volume y. What I'm trying to say, there are two volume here. One volume is keep y constant and do like this. It forms a volume. Second is keep x constant and move like this. Underneath is the volume. Or I do like this, it will be clear. Underneath is the volume. If I do together, then this volume or this volume, if I keep x constant and do like this will be 1 by 2 dz by dy into y square into x. If I do this together, then it will be like this and this. Then I have to sum both of them. Since it is a straight line, there is no other component I see here. So it is like 1 by 2 bracket, 1 by 2 and in bracket dz by dx into x plus dz by dy into y bracket close into xy. That is the volume I have to subtract now. F00 into xy minus 1 by 2 in bracket dz by dx x plus dz by dy y bracket close into xy. This is what I have to subtract now. If I subtract, then I am near to it. Same thing the way we were doing in the xy plane. Same. In xy plane, we were doing like this. And first I subtracted a triangle and then next. Now it will be come to a second differentiation. If I talk second differentiation, then it will be little complex. It is not that straightforward that if I take dual differentiation with x-axis, if I take dual differentiation, if means if this is the surface, consider this is the surface, and if I cut in xz plane, then if I take dual derivative, then I have one surface area. If I cut in yz plane and if I take dual derivative, I have a surface area. What about if I cut in any other plane? I cut in a plane where we have dz by dx and dz by dy. Right now, dual derivative in xz plane means d2z by dx square, d2z by dx square, and d2z by dy square. That is a dual derivative. Okay, is it possible that there will be a derivative, that there will be a component that will be in single derivative of x and single derivative of y? What I'm trying to say is dz by dx and dz by dy. That component is also there. Yeah, certainly it will be there. Okay, what I'm trying to say is if I move like this, then it will not be a smooth the way it was in a flat line I did. If I do if it is like this and if I move like this is what the volume I calculated now. But if it is a double differentiation, then double differentiation will exist if there is a correlation between x and y also. It is little complex. Okay, how to solve it? Means only if I say what I'm trying to say is if I go for single derivative, then this is the flat line I'm talking like this. But if I go for double derivative, then it will resolve into z equal to x square and z equal to y square. If I rotate like this, then it will form a very odd kind of surface, which will have a component in dz by dx into dz by dy also. Okay, then how to find that? For that, let's analyze more towards it. We are sure that for first component, that is the cuboid area, the volume is actual volume is fxy dx dy. That is the actual volume. But now we are estimating the volume with the dividing the volume into n different parts. This is what we are doing. N different parts. The first part is the actual cuboid. F00 into xy. Xy plane is the area in the xy plane. F00 is the height of the surface at point x is 0, y is 0. That is the volume. Second is 1 by 2 and then in bracket dz by dx at x equal to 0 into x plus dz by dy at y equal to 0 into y and in bracket x into y. If I compare with single dimensional Taylor series, then it is equivalent to 1 by 2 dy by dx into x, dfxy by dx into x into x, 1 by 2. That is similar as 1 by 2 and then 1 dfxy by dx into x plus dfxy by dy into y in bracket x into y. X into y is the xy component. That is the independent component. Now, and there x was independent. So x is termed at x into y. All right. 1 by 2 is 1 by 2. All right. That x, middle dfxy by dx into x, it became dfxy by dx into x plus dfxy by dy into y. Looks like x is similar to x plus y here. Dfxy by dx is renamed. Last x become x into y because that there x was independent variable. Here x into y is independent variable. So that is all right. Okay. Now first is 1 by 2, 1 by 2, 1 by 2. All right. Next is dfxy by dx into x. Here dfxy by dx into x plus dfxy by dy into y. So x is x plus y out here. Okay, in that fashion, we have to take another component as x plus y whole square. X plus y whole square. Okay, how to proceed now? Calculating the volume of the second component. What we are saying, I had to calculate volume of the surface underneath it, but I calculated the volume of a full cuboid. Then I said, I'm sorry. Then the triangular region I subtracted it. Now dual differentiation region I have to subtract. For subtracting the dual differentiation region, what we did in single component. In single component we did is 1 by factorial of 3. 1 by factorial of 3 d2 by dx square into x square into x. Okay, in similar fashion, you will do like this here also. But there it is x square, here it will be x plus y whole square. Okay, what is x plus y whole square? X square plus 2xy plus y square. 2xy, 2 is a constant that I can leave now. Means 2 as a constant, later I can divide it by 2. So 2 is not a big thing. I can just remove it, not required. X square plus xy plus y square. This is the component that is related to xy, x square in the 2D case. If someone is very smart in mathematics, he can find out the correlation if I'm taking the dual derivative. Then d2 fxy by dx square is the first side, and in yz plane d2 fxy by dy square is the dual derivative in that side, and in correlation to these two there will be a component dfxy by dx into dfxy by dy. Okay, if I was taking single diagonal, then it is dfxy by dx, dfxy by dy, and in correlation of them, it will be dfxy by dx, zero, first differentiation, first differentiation. Then if I take correlation, then minus 1, zeroth differentiation and zero, so doesn't make any sense. Here, double differentiation, double differentiation. In correlation, we have single differentiation and single differentiation. That is similar as x into y. That is similar as x into y component. Now let's settle down what we have done prior to it. Prior to it, we have done x square. So for x square, it will become 1 by factorial of 3 d2 fxy by dx square into x square. That will be the component that will be formed with the x square. For the y square, the component that will form the volume component. For volume component, how we are calculating volume component? If someone is very avid watcher, then how we are calculating the volume component? If this is a flat line, I am trying to calculate the volume that is created because of this triangular region. Then first we calculate the triangular area and then multiply by the y. Or if I keep x constant and if I do like this, then this is the triangular region. I'm sorry. If I keep y constant and I move like this is area of triangular region. XZ plane, I calculate the triangular area. I multiply by the y. If I keep x constant and move y, then this is the triangular region in YZ plane. I calculate the area of this triangular region and multiply by x. Similarly, if I have two dimensional, two dimensional, then this instead of flat line, if I keep y constant, then it won't be flat line. It will be like this, x squared. Okay, if I keep x constant, then it will be like this. That will be y squared. Okay, or in this fashion, if I take in other way, y squared. This is x squared. If I have to calculate this area and then multiply by y, or I have to calculate this area and multiply by x. Okay, okay, if I am calculating this area, then more or less it will come as whatever you calculate multiply by xy. The way we did in two dimensions, you calculate the area and then you calculate the height, that will be a constant, and multiply by x, you will get the area. Here you calculate the more or less height and multiply by x into y. Make sense? The way we did in the two, if I take again the second part, first part is f00 into x into y. F00 into x into y. X into y is the area. Next part is 1 by 2. 1 by 2 in bracket dfxy by dx into x plus dfxy by dy into y into xy. Xy is the area. Third part, if we are taking, then it will be in something x plus y whole square into x into y. Okay, now if I break x plus y whole square, it will be x square plus 2. I'm leaving it, x into y square. To settle, this is the vertical part. If I do dual differentiation of this, I'll get a vertical part multiplied by x into y to calculate the volume. What will be dual differentiation part of x square? If I see the single dimension Taylor series, then it will be 1 by factorial of 3 d2fxy by dx square at x equal to 0, y equal to 0 into x square. Makes sense? Plus x into y. X into y will become dfxy by dx. dfxy by dx into x in hop. It is just x, right? So it will become dfxy by dx into x by factorial of 2 into dfxy by dy into dfxy by dy into y at dfxy by dx at x equal to 0, dfxy by dy at x equal to 0, y equal to 0 into x hop into x by factorial of 2 and then into y by factorial of 2 plus y square, that will become 1 by factorial of 3 d3 d2 fxy by dy at x equal to 0, y equal to 0 into y square, and outside we have x into y. If I settle it down, it becomes 1 by factorial of 3 d2 fxy by dx square at x equal to 0, y equal to 0 into x to the power 3. X square was there multiplied by xy into x to the power 3 into y plus 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 1 by plus d fxy by dx at x equal to 0, y equal to 0 into x square y into x square y. I'll rephrase this. I I'm sorry. Okay, looks like we are making some mistake. Okay, so or it is all right. Okay, we'll try again. First part is 1 by factorial of 3 d2 fxy by dx at x equal to 0, y equal to 0 into x to the power 3. Earlier it was x square multiplied by xy outside, x to the power 3 into y. Next is dfxy by dx. I'm not saying x equal to 0, y equal to 0. It is already there. dfxy by dx into x by factorial of 2 into dfxy by dy into y by factorial of 2 into x into y. So x square y square plus 1 by factorial of 3 d2fxy by dx dy square into y to the power 3. This will become the next component. Okay, someone can try. Then what will be the next component? The next component what we are seeing, that will be x plus y to the power 3 into x into y. Now I have to break it, x to the power 3 plus 3x square y plus 3xy square plus y to the power 3. If I settle down x to the power 3, it will come 1 by factorial of 4 d3fxy by dx into x to the power 3 plus d2fxy by dx square into x square by factorial of 3 into dfxy by dy into y by factorial of 2 plus 3 I am not keeping now plus dfxy by dx into x by factorial of 2 into d2fxy by dy square into y square by factorial of 3 plus d3fxy by dy square dy3 dyq into x to the power 4 into x to the power 3 by factorial of 4 bracket into x into y. Someone has to settle down. This way it will proceed multivariate in the volume. Okay, if I have calculated the volume, now I have to differentiate it by dx dy. The left hand side is fxy dx is the volume. If I'm calculating the volume, if this is fxy, the underneath volume, if this is xy plane, the underneath volume is dfxy. If this is the fxy, the underneath volume is fxy dx dy. That will come as, if I do dual difference integration fxy dx dy. If I do double differentiation, it will become fxy only. Fxy equal to f00 into x into y. Xy will go away and it will become f00 plus plus 1 by plus 1 by 2 plus 1 by 2 and then dfxy by dx into x square into y. If I do differentiation with x and y, 2 will go away and y will go away, only x will remain. Dfxy by dx into x plus dfxy by dy into y, that will remain. Plus, now we have 1 by factorial of 3 d2fxy by dx square into x to the power 3 into y. If I differentiate with x, it will become 3x square. 3 go away. It will become 1 by factorial of 2 d2fxy by dx square into x square. Y will go away. Only x square will remain. Let's see the another one. Another one, we have dfxy by dx, and then dfxy by dx at x equal to 0. So that is a constant into x square into y square. If I differentiate x square, it will become 2x. If I differentiate y square, it will become 2y. I have to differentiate with x and y. 2 go away, 2 go away. There is no denominator now. Denominator was factorial of 2, factorial of 2. It will become 1 gone. So it is dfxy by dx at x equal to 0, y equal to 0 into x dfxy by dy, or altogether I can say d2fxy by dx dy into x into y plus 1 by factorial of 2 d2fxy by dy square into y square. That will remain. I think so, yeah. Plus, now someone can proceed like this. And this way, through volume way, dividing the volume into n different parts. First part is the flat volume. Second part is that I have to subtract the triangular volume. Third part, I have to subtract the quadric, means power 2 volume. Third part, like that. If I divide into n different parts and dividing into n different parts, indeed we can calculate the multivariable Taylor series through the volume fundamental. Amazing, mind-blowing. Something that will take someone's chair out. Okay, this proof is not available in any of the book. Anyone can say. Anyway, please do not mind supporting us. +91 is the India country code 9483160610 is the telephone. +91 is the India country code 9483160610 is the telephone number.